So good afternoon. This is lecture 6 of the course entitled An Introduction to Linear Algebra Using Python. My name is Dr. Richardson, and my email address is listed below as srichards22@comcast.net. So as a reminder, learning is not a passive activity. Rather than just watching me give the lectures either in real time or recorded versions, you need to take lecture notes in either venue. By taking the notes and writing down the discussions and equations line by line, that is the way that you will learn what's going on. So learning is not a passive activity. Need to do the problem sets. So as of today, problem sets 1, 2, 3, 4 are all posted. Their solutions are all posted. Problem set 6 will be posted tomorrow, and video clips of lectures 1, 2, 3, 4, and 5 are all posted. Today's lecture 6 should be posted sometime in the next day or two. You're encouraged to ask questions. So at the end of today's lecture, we have a recitation section. So if you have any questions, I'm available then, and also after course. So if you have a question on the problem sets, the lectures, our problem set solutions, typos, etc., just shoot me an email, and I promise to get back to you within 24 hours with a response. And a ruler is certainly useful in taking notes and really going through problem sets. So today's lecture, we'll continue with our review of vector analysis. We'll talk about vectors in R1, that is a line, R2, that is the plane, and R3, that's three-dimensional space. We'll talk about the idea of linear independence and linear dependence and independence of vectors. And finally, we'll finish up with a discussion of the fact that vectors really are matrices. So everything we've talked about heretofore about matrices will be applicable in our discussion of vectors. Okay. So last time we talked about vectors in one dimension. We should probably start this afternoon about talking about vectors in 2 dimensions. And again, as I said, this is a review of vector analysis. So I'm probably going to tell you some things that you already know, and maybe even tell you some things you don't know. I also highly recommend, and it's listed in problem set 6, which will be posted by tomorrow, Grant Sanderson's excellent visualization lectures on the essence of linear algebra. They really are very beautiful visualization lectures of many of the key ideas. We're not going to discuss everything that Dr. Sanderson discusses, but a few of his lectures are very pertinent to what we're talking about. And I will guide you to the appropriate lectures on the problem set. So let's talk about a vector in 2 dimensions. I can write it in coordinate form. It has 2 components, v sub x and v sub y. And it turns out I can also write it using the ideas of scalar vector multiplication. So I can take the scalar v sub x and multiply it by a unit vector I sub hat, and then take the scalar v sub y and multiply her by a unit vector j sub hat. And the scalar multiplication is interchangeable, commutative, so I could write this in this form. Again, unit vectors are vectors that point in a particular direction, and they have magnitude of 1. And as we did in last lecture, I will point out that there will be times when it's useful to recognize there are alternate ways to write these unit vectors I hat and j hat. You can either write them as e hat 1 or e hat 2, and why we want to even worry about that will become clearer later. So again, not drawing the scale, I hat is a vector that points in a positive x direction. J hat is a vector that points in the positive y direction. I hat points in the positive x direction. J hat points in the positive y direction. And both of these vectors have magnitude of, or norms or lengths of 1. That's why they're called unit vectors. So vectors are creatures that have magnitude and direction. Here's where I specify the magnitude, and here's where I specify the direction. Or alternatively, I can use this notation of E hat 1 and E hat 2 for my unit vectors. And that should be that. Note that my set of parallel vertical bars is the norm. That's the notation I'll use for the norm, the length, or the magnitude of a vector. That's distinct from just 2 sets of vertical bars, which represents the absolute value of something. And so those are different things. Okay, so now that we've discussed what this looks like analytically, what does it look like geometrically? Well, here's where my ruler comes into play. So I have an x-axis and a y-axis, and consider a vector v that goes from 0, 0, which is its tail, to its head. Starting at the head, if I draw a line that's perpendicular to the x-axis, and draw another line from the head or the head of the vector v to the y-axis, I'm able to define these components or coordinates v sub x and v sub y, where again, I have a set of unit vectors, I hat and j hat, that tell me what the directions are in this particular geometry. Okay, so really, if you ask yourself, what is the magnitude of this vector v, you could take a ruler and measure it. But a more convenient or analytical way of doing this is simply to take the vector v, dot it into itself, and take the square root of that. And by definition, that's just the component v sub x squared plus v sub y squared. Add those two together, take the square root, and you'll get the magnitude, norm, or length of the vector v. And note that this is always positive. It's 0 for the case where both of these coordinates are 0. Both of these components are 0. So I want to introduce something which we already know, but I'm going to say it a little bit more clearly. The set of all real points, and remember, points are vectors, vectors are points. We talked about that last lecture. So the set of all real points or vectors generated or spanned, that's an alternative word, by my unit vectors, E sub hat 1 or E sub hat 2, has a name. It's called R superscript 2. And that's just a fancy way of defining the plane in 2 dimensions. This set of unit vectors is called a basis vector, or basis vectors, plural. In the 1-dimensional case, we had R1, which was just a line, and it was generated by a single basis vector, E hat 1 or I hat, and all points in the plane are defined by this creature R superscript 2, and they are generated or spanned by 2 basis vectors, E hat 1, E hat 2, or I hat, J hat. So it is very useful to keep track of this convention where you can use E hat 1 or E hat 2 in lieu of I hat, J hat. You may not see the advantage of it now, but we'll get to that later. Sometimes these basis vectors are called standard basis vectors. And that's really it for life in 2 dimensions, as far as vectors are concerned. So the next logical jump we'd like to make is, what happens if you have a vector? And so this would be case 3. What happens if you have a vector in 3 dimensions? So if you have a vector in 3 dimensions, excuse me 1 minute. Sorry, if you have a vector in 3 dimensions, like 3-dimensional space, it has 3 components: v sub x, v sub y, v sub z. And you could also write this as the sum of 3 creatures. Each one of these creatures involves multiplying a scalar by a vector. And the vector in this case is a set of unit vectors. So you could write a vector in 3 dimensions as I hat v sub x plus j hat v sub y plus k hat v sub z. And again, here I'm multiplying a vector times a scalar. That's the same as multiplying a scalar by a vector. So you would write these in this fashion, and it would be equivalent. So again, here I've introduced a third basis vector, I hat, j hat, and k hat. So these are basis vectors. Clearly, k hat is a unit vector that is perpendicular to the plane contained by I hat and j hat. So in 3 dimensions, I have 3 basis vectors. And again, I'm going to go back to this convention. They are I hat, j hat, and k hat, but I could also write them as e hat sub 1, e hat sub 2, e hat sub 3, for reasons that we'll talk about later. Okay, so these basis vectors, or they're really unit vectors because they all have magnitudes of 1, or unity. And again, I could write this in an alternate form. The magnitude, norm, or length of e hat 1 equals the magnitude, norm, or length of e hat 2 equals the magnitude, norm, or length of e hat 3, which equals 1. So I will, as I did before in the case of 3 dimensions, write down a statement that pulls all of this together. The set of all real points generated or spanned, both those words are equivalent, by my unit vectors e hat 1, e hat 2, and e hat 3, we will call that r to the 3rd power. And that's just another fancy way of writing 3-dimensional space. Okay, so you should note the following: that e hat 1, e hat 2, and e hat 3, or I hat 1, I hat, j hat, k hat, these are called, again, the standard basis vectors. So they're unit vectors, and they're, in particular, they're basis vectors, because any vector in 3 dimensions can be generated from e hat 1, e hat 2, and e hat 3, where e hat I dotted into e hat j equals Chronicler Delta ij. We've seen this creature before, last lecture. This is Chronicler Delta. So what is this? It's a very convenient shorthand way of saying that if I equals j, the subscripts I and j are equivalent, then this creature is 1. And If not, then it's 0. So again, I refer you to problem set 6, which will be posted tomorrow, which gives you a good reference, gives you links to Grant Sanderson's lectures, the appropriate lectures, in which he shows really beautiful, spectacular visualization lectures on unit vectors and how to span or generate a line, a plane, or three-dimensional space. And again, you'll get practice with this in problem set 6, but Dr. Sanderson can do this much better than I can. And so I highly recommend looking at his visualization lectures. Also, Sal Khan has some nice lectures also on vector analysis if you feel you need to brush up on this. Okay, so we're talking about vectors. And at this point, it's going to be interesting to recognize that vectors have some other interesting properties. Namely, they can either be linearly independent or linearly dependent. So I want to tackle these ideas and see how they're useful, first in a discussion of vectors, but ultimately how they're helpful in linear algebra. Okay, so let us consider two vectors in R2. And it's, sorry, sloppy on my part. This R is typically written with two vertical lines. And R2 is just a fancy way of talking about a two-dimensional plane. So let's look at case 1. So here's where my ruler comes into play. Let me just consider two vectors. One is A, and let me consider another vector that has the same tail, and we'll call this vector V. Vector B, as in boy. So we have introduced the idea of a linear combination of vectors. So we could write down a linear combination of these two vectors as follows. We could define a new vector, which we'll call W. And I'll write this down, and I'll come back and say what it means in a minute. This is what I mean by linear combination. Namely, you give me a vector A, and you give me a vector B. You give me two scalars, C1 and C2, and these scalars are real. They're real scalars. And then I can use the idea of scalar multiplication. I can multiply the scalar C sub 1 times the vector A, scalar C sub 2 times the vector B, get a vector, and add the two together to get another vector. This is a linear combination. And the point that we want to pay attention to here is that all points in R2 can be expressed as a linear combination of A and B. All I have to do is come up with different numbers for C1 and C2, and I can generate any point in the plane. Okay. And again, please look at Dr. Sanderson's videos. They're outstanding. Now, in the second case, I want to pick two vectors. Here's a vector A. I'm going to pick another vector that has the same tail, but the second vector, which I'm going to call B, is coincident on A. Okay. In other words, B, the vector B, is a multiple of A. So what's going on here is that these two vectors A and B, when I take linear combinations of them to get a new vector W, so this is what I mean by linear combination. And I don't need this subscript here already. These vectors do not span or generate all of the plane. If you take a linear combination of these two, so let me go back and do what I said I was going to do. That subscript is not there. So something is happening, something is going on that's different in case one as opposed to case two. These vectors do not generate all points in the plane. They only span or generate points in a line, R1. Okay. So what is going on here? What's the difference between what we see at play in case one and what's the difference with what we see in play in case two? So we're going to go back and look at these cases a little bit more carefully. Well, let's go back to, so let us revisit case two. And I'm going to use different symbols in my vectors. That's okay. So here's a vector which I'll call v sub 1. And here's another vector which starts with the same origin, which I'll call v sub 2. So as I said before, when we looked at case two, v sub 2 is really just a scalar multiple of v sub 1. V sub 1 could be a vector that has a magnitude of 10, and if the scalar is 2, then the magnitude of v sub 2 is 20. And here, my scalar alpha is not 0, so it's a non-zero scalar. Could be negative for that matter. So I want to take this fact that v sub 2 equals alpha times v sub 1 and look at this and ask myself, what's going on here? Well, what's going on here is that v sub 2 is dependent on v sub 1. Clearly, that's what the equation tells me. Furthermore, not only is it dependent on v sub 2, but it's linearly dependent on v. Not only is it dependent on v sub 1, but it's linearly dependent. V sub 2 is linearly dependent on v sub 1. Why is it linearly dependent? Well, I don't have v sub 1 raised to a power. I'm not taking the square root of it. I'm not taking the hyperbolic cosine of it. It's just dependent on it, where v sub 1 is just raised, if you will, to a power of 1. So if I take this expression and rewrite it, the thing on the left-hand side, now let's be careful. Excuse me, let's be careful. I might be tempted to just write 0, but that's a problem, right? Because here's a vector, I'm subtracting two vectors, so this thing on the right-hand side, it better be a vector. So it is the 0 vector. And strictly speaking, the 0 vector is not the same thing as the number or scalar vector. You may say that's a fine point, but it's an important fine point. Okay, so if we put all this together, if I have two vectors, v sub 1 and v sub 2, for this expression, which we'll highlight in red because it's so important, for this expression to be true, neither C1 or C2 are both 0. And we clearly see that from the case here. So this is a definition of linear dependence. Namely, if you have two vectors, v sub 1 and v sub 2, and if they satisfy this equation, only if both of these coefficients, c sub 1 and c sub 2, are not 0, then we say that these two vectors are linearly dependent. We're going to go through some examples of this in a minute, so just hang tough. So let us just say in general, a set of n, 1, 2, 3, 4, 5, 30, 10, a million, a set of n vectors is linearly dependent if and only if, it's too many words and the mathematicians just abbreviate that by IFF. This expression is true, c sub 1 scalar times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3 dot 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 c sub n times v sub n equals the 0 vector when at least one of the coefficients, one of the c sub i's, does not vanish. And that's clearly the case for this simple example here. For this simple example here, this coefficient of v sub 1, which we call c sub 1, is minus alpha. So linear dependence means that one vector really is a scaled version of another vector. Or if you have a set of vectors, they satisfy this equation where at least one of the c sub i's, c sub 1, c sub 2, c sub 3, c sub a million, does not vanish. Okay, so to hit home the idea of linear dependence, let us revisit case 1, the other situation. And that was a situation where we had two vectors. And again, I'm going to rename them. So one is v sub 1, one is v sub 2. And if you look at these two vectors, sorry, being a little sloppy. So v sub 1 has its tail at the origin at some point, and from the origin, I'm also going to define a vector v sub 2. And if you look at these guys, just look at them, stare at them, they are definitely different from what's going on in case 1, or case 2. So what's different? Clearly, V sub 1 does not depend upon V sub 2. There's no way in the world that you could write V sub 2 as some scalar times V sub 1. That's not going to happen. Thus, the only way C sub 1 times V sub 1, C sub 1 is a scalar, V sub 1 is a vector, plus C sub 2 times V sub 2, the only way this is going to equal the zero vector is if all of my coefficients, all C sub I coefficients, vanish. If this is true, and again, let's highlight this in red. These vectors, in this case for two examples, for two vectors, these two vectors are linearly, run out of space. Independent. So linear dependence and independence, these are important ideas that have a geometric interpretation. So here are two vectors that are, let's say, V sub 1, V sub 2. These guys are linearly independent. And they satisfy this condition where at least one of these one of these coefficients, C sub I, doesn't vanish. And you can contrast that with the situation of linear dependence, where one vector literally depends upon the other. And in this case, for two vectors, the only way that this is going to be true is that all the coefficients C sub I have to vanish. So I'm going to go through an example of this. Before I do that, I'll just make a final useful statement. And we'll see how all this works in an example. So the statement I'm going to make is, I've been looking at two vectors, let me look at three vectors. So suppose you have a set of three vectors. And let's call them V sub 1, V sub 2. I can call them anything I want, but let me just be a little logical here. We call them V sub 1, V sub 2, and V sub 3. And there's a relationship among these three vectors. Suppose one is a linear combination. And we know what that is. We've talked about that. We did that back in lecture 5. So one of these vectors we're saying is a linear combination of the others. That means that you could take, for example, V sub 1 and express it as the sum of the coefficient C sub 2 times V sub 2 plus C sub 3 times V sub 3. You could rewrite that as V sub 1 minus C sub 2 times V sub 2 minus C sub 3 times V sub 3. And this equals not the scalar 0, but the 0 vector. And if all of this hangs together, these vectors are linearly dependent. Since at least one of the coefficients C sub I does not vanish. Okay. All right. So you will have practice with these ideas of linear dependence and linear independence of vectors on in problem set 6. But I want to go through an example in lecture. So suppose I give you 3 vectors, v sub 1, v sub 2, and v sub 3. So the question I want to ask is, are these 3 vectors linearly independent? So that's the question. You can get an answer by just looking at the equation that we talked about and studying what it means. So what am I talking about? Under what circumstances does a constant or coefficient c sub 1 times v sub 1 plus c sub 2 times v sub 2 plus c sub 3 times v sub 3, under what circumstances does that equal the 0 vector? And again, this has to be a vector here. This is a vector. This is a scalar times a vector. That gives you a vector. Scalar times a vector gives you a vector. Scalar times a vector gives you a vector. So therefore, this thing must be a vector. So under what circumstances is this equation true? If it turns out it's only true if all the coefficients C1, C2, and C3 are 0, then the 3 vectors are linear independent. You can go home. Otherwise, they're linearly dependent. So to answer this question, let's use our knowledge from lectures 1, 2, 3, 4, and 5 of matrices or matrix algebra. We've learned a lot. I said before many, many times, this course is cumulative. You can't jump into lecture 6 without making sure you've mastered the ideas of lectures 1 through 5. So let's look at this equation. We'll call this one equation. And let's look at this equation. And let's put these things together. This equation that has the double asterisks tells me that C sub 1 times V sub 1, which is just 1, 0, 0, plus C sub 2 times 1 minus 1, 1, plus C sub 3 times 1, 2, minus 1 has to equal the 0 vector. So the beautiful thing about this equation is that you can express this as, wait for it, a set of linear equations. All you have to do is look at this equation, 3 stars, and see what it's telling you. It's telling you first that C sub 1 plus C sub 2 plus C sub 3 equals the number or scalar 0. Excuse me. I just get that by multiplying C sub 1 by this 1, adding that to C sub 2 times this 1, adding that to C sub 3 times this 1, and equating that to the 1, 3 component of the 0 vector or matrix. We'll see later on that matrices are vectors, but let's jumping ahead a bit. Second equation I can get is 0 minus c sub 2 plus 2 times c sub 3 equals 0. And the third and final equation is 0 plus c sub 2 minus c sub 3 equals 0. So what do we want to do? I have a set of linear equations. I have 3 unknowns, and I can solve these using everything I've learned so far. We have seen this movie before. Namely, I can write down the coefficient matrix for this problem. It's just 1, 1, 1 first row, 0, minus 1, 2, 0, 1, minus 1. I can write down the constant matrix for this problem. B is just 0, 0, 0. I can build my augmented matrix, by just gluing these things together. 1, 1, 1, 0, 0, minus 1, 2, 0, 0, 1, minus 1, 0. And what we want to do is simply use Gauss-Jordan elimination to find my unknowns, which is in this case are c sub 1, c sub 2, c sub 3. I claim that once I know that, I'll be able to determine whether or not these original vectors v sub 1, v sub 2, and v sub 3 are linearly independent or not. Okay, so let's get started. Again, we've done this. We're experts in this. So let's write down the augmented matrix. And I essentially want to write this in reduced row echelon form. So what I will do, first row is 1, 1, 1, 0. Second row is 0, minus 1, 2, 0. Third and final row is 0, 1, minus 1, 0. Okay, so the leading 1 is okay in row 1. Row 2, I have a problem. I have a minus 1, not a 1. I want to turn that to a leading 1. So let's multiply row 2 by minus 1. So that becomes 0, 1, minus 2, 0, 0, 1, minus 1, 0. Next, I need to turn this 3, 2 matrix element into 0. So the best way to do this is take a Xerox copy of row 2 multiplied by minus 1 and add that to row 3. So row 1 is left alone. Row 2 is left alone. I just took a Xerox copy of it. But row 3 becomes 0, 0, minus 1, 0. So I have a leading 1 in row 1. I have a leading 1 in row 2. Row 3, I almost have a leading 1. Okay, so in the interest of time, I'm going to let you continue. And so at the end of the day, you'll get your, so you should show that after a number of elementary row operations, you can put this problem in reduced row echelon form. Okay. Okay, having done that, we start from the bottom and work our way to the top and write down the corresponding set of algebraic equations. And they would be c sub 3 is 0, c sub 2 is 0, C sub 1 is 0. So this tells me two things. It tells me there's a solution to the problem, tells me that the solution is unique, and it tells me the solution is the trivial solution, that C sub 1, C sub 2, and C sub 3 are all 0. But more importantly, we go back to the definition of linear independence. The three vectors that we are studying V sub 1, V sub 2, and V sub 3, in this case, they all are linearly independent. And the reason why that's true is that this equation we have shown explicitly by using Gauss-Jordan elimination that this equation is only true so this equation is only true if and only if all the coefficients vanish. Okay. So alternatively, if you went through another problem and determined that one of the coefficients didn't vanish, then that would imply that the vectors that you were given were linearly dependent. So we're going to take a break in a minute. But again, going through lots of examples and determining whether or not a set of vectors are linearly dependent or independent, it's a useful exercise. It's a useful tool. It's a useful technique that you need to master. And the good news is that you don't have to learn any new techniques to do this. Gauss-Jordan elimination comes to your rescue, and all you have to do is solve for under what conditions this equation is true. So let us break for 5 minutes, stretch our legs, and come back at 2:50. Okay, so let's resume. So we have defined what we mean by the linear independence of a set of vectors. We've defined what we mean by the linear dependence, of a set of vectors. And we've even come up with a way of determining whether a set of vectors are linearly independent or not. And we didn't need any new machinery. We just used our old friend or friends, Gauss and Jordan, two individuals, two great mathematicians. And again, problem set 6 gives you lots of progress, lots of practice with these ideas. And Grant Sanderson's appropriate videos, which are referenced in problem set 6, which should be available tomorrow, are also beautiful ways to see in pictures what these concepts are telling us. So it begs the question, you've gone through the trouble of introducing these two new concepts. What do they have to do with everything else we've talked about so far? Why is this useful? So I would like to go back and revisit some examples that are simple, that we've talked about in this course, where the amount of calculation we need to do is relatively minimal, so we can look at the results and sit down and see what they're telling us. So recall this example of two linear equations, two unknowns, and you could either use Cramer's rule or Gauss-Jordan elimination to solve this system of linear equations. I will use the latter. I will use Gauss-Jordan elimination, so I'll build the augmented matrix, which looks like this, and I'll write it in I'll transform it into reduced row echelon form using the appropriate elementary row operations. So it would seem to me that you would want to take a Zeroth copy of row 1, multiply by -1, add that result to row 2. That will give you a matrix that has row 1 that looks like that, and row 2 looks like that. The next thing you'd want to do is turn the leading 1 in row 2 into a 1. So you can do that by just dividing row 2 by the number 3. So that would give you this. The remaining thing you need to do is recognize that you've got your leading ones in row 1 and row 2. For this leading 1 in column 1, all the other matrix elements are 0. In column 3, your leading 1 is here. It's in the 2, 3 position, but you've got to turn that 2 into a 0. So let's take -2, multiply it by row 2, and add that to row 1. And that should give you 1, 1, 0, 0, 0, 1. And this is in reduced row echelon form. And now that you've achieved that, all you have to do is start from the bottom, work your way up, and write down the corresponding set of algebraic equations. So nothing we've done so far is new. In fact, we've done this at least twice before. And so what would they be? Well, they would be that x of 2 times 0 is 1, and x of 1 plus x of 2 is 0. So clearly, there is a problem with this first equation, because there's no scalar x of 2 that you could multiply 0 by and get the number 1. So using Gauss-Jordan elimination, in this particular problem, no solution exists. And furthermore, we've talked about the idea of the rank of a matrix. So if you calculate the rank of the coefficient matrix and you calculate the rank of the augmented matrix, you will find that these are 1 and 2 respectively. So the fact that the rank of the coefficient matrix is less than the rank of the augmented matrix is another confirmation that no solution exists for this simple problem. There is no set of values for x and y that'll solve these two equations simultaneously. You can almost glean that by just looking at it, but you've proven it rigorously for a simple example. Now, that's all new. That's old news. New news. Let us study the augmented matrix, or the coefficient matrix rather, which is a 2 by 2 matrix. It's a square matrix of order 2. And let's recognize that this matrix has 2 rows and 2 columns. First column, C sub 1, second column is C sub 2. But look at that first column. That's really just a vector, which we'll call C sub 1. The second column is really a vector also. We'll call that C sub 2. And if we look at the relationship between these two vectors, it's clear that C sub 1 can be obtained by just multiplying C sub 2 by the number 1. In other words, C sub 1 and C sub 2 are linearly dependent. Now, let's calm down a bit. This is by no means a proof, but at least for this simple example, it's suggestive of the observation that when you have a matrix A, that's the coefficient matrix of a problem, and it consists of two column vectors, C sub 1 and C sub 2, and those guys are linearly dependent, then this simple example suggests that there is no solution to the problem, regardless of what the constant matrix is. And that's sort of interesting. So that's just an observation, okay? So let's look at another example, see if we can get some insight from that. So this was example 1 we just worked out. And again, these are problems we've seen before, so that we don't have to spend a lot of time on the details. Let's look at example 2. Here are two equations and two unknowns. And again, I want to solve this to find out what X and Y are. And you could argue, you could almost guess by looking at it, but that's not the point. So in this particular example, the coefficient matrix just looks like this. The constant matrix looks like this. I can pick up the pace a bit because we've done this many, many times. We're using Gauss-Jordan elimination to write this augmented matrix, which is this, in the form of reduced row echelon form, from which we should be able to read out the solutions. So I would say the problem is this 2-1 matrix element. That's the problem. So let's take a 0th copy of row 1, multiply it by -2, add that to row 2, and we should get the following result. First row is 1, 1, 2. Second row consists entirely of all zeros. And again, go back and refresh your memory. This is now in, according to our definitions, this is definitely in reduced row echelon form, because I have a row of all zeros, but I put it at the bottom. So everything is fine. So again, you've seen this problem before. The corresponding set of algebraic equations I can obtain by starting from the bottom and working my way up. And they would be the 0 times x sub 2 is 0, and x sub 1 plus x sub 2 equals 2. So the first equation tells me that x sub 2 can be anything. Any number, any scalar times 0 is going to be 0. And x sub 1 is just going to be 2 minus, x sub 1 is 2 minus x sub 2. So x sub 1 is related to x sub 2. X sub 1 you can get by just using this expression. But x sub 2 can be any number you pick. So if x sub 2 is 3, then x sub 1 is -1. But you can pick any value for x sub 2 you want, and both of these algebraic equations are satisfied. So that tells me that an infinite number of solutions exist in this problem. We've talked about the idea of a rank, and you know how to calculate the rank of a matrix. So you can calculate the rank of the coefficient matrix. You can calculate the rank of the augmented matrix, and you'll find that both of those are equal to 1. And if you put these things together and try to figure out how are they related, it'll turn out that the rank of the coefficient matrix is 1, the rank of the augmented matrix is 1, and both of these are less than 2, where 2 is the number of unknowns in the problem. X and Y, I have 2 unknowns. And so that's consistent with what we saw before when we defined this idea of a rank and what it tells us about a problem, whether it has a unique solution, an infinite number of solutions, or no solution. Okay, so this is all old news. Now let's get to the new news. What about the coefficient matrix A? Is there anything interesting that I can discern by looking at this matrix? Well, first of all, it's a square matrix of order 2. But again, using the same analysis as I did before, it really consists of 2 column vectors, C sub 1 and C sub 2. Sorry, typo. And what's the relationship between these 2 vectors? So we're looking at a matrix from a different point of view now. We're looking at a matrix that has columns. We're viewing the columns of a matrix as vectors. And in this case, these 2 guys are linearly dependent. Again, because one is just a multiple of the other, and that multiple is just a scalar 1. So again, this is not a proof, but this particular example suggests that when you have a coefficient matrix like A, and you have columns in this matrix that are vectors, and these vectors are linearly dependent, that if you use this coefficient matrix in a problem to actually solve for a set of unknowns, no matter what the constant matrix is, like in this example, that you will have an infinite number of solutions or no solution. So again, it's not a proof, but it sort of suggests that, when you look at a matrix B, and if in fact you write it down, you should be able to prove to yourself that these 2 columns, 1 and 2, represent vectors, but those 2 vectors are linearly dependent. They depend upon each other. So in fact, if you were to, well, let's change it a little bit. Let's make this 8. Okay, right. So I'm happier with that example. So I make this 8. So the fact that in this example that C sub 1 and C sub 2 are linearly dependent, and you should be able to prove that that's the case, that would mean that if in fact you use this problem as a coefficient matrix in a problem where you are trying to find a solution to a set of linear equations, that you would not get a unique solution. No unique solution exists. Okay, so my third example, and again, this is a system of equations we've seen before. It's going to be simple to write down so that we can not spend a lot of time with the analysis. So I want to solve this problem. I want to solve this problem for X and Y, and I want to do it using Gauss-Jordan elimination. So the coefficient matrix is just 1, 1, minus 1 in row 1 and row 2 respectively. The augmented matrix I can write down That's just 1, 1, 2, 1, minus 1, 4. And you know how this game is played. I have to come up with elementary row operations such that I can turn the augmented matrix, or write the augmented matrix in reduced row echelon form. And here I picked an example where the number of elementary row operations is pretty easy. So let's go through this. Let's just take a Xerox copy of row 1, multiply it by minus 1, add that result to row 2. Row 1 is not changed. Row 2 is certainly changed. She becomes a 0, minus 2, 2. I have a leading 1 in row 1. I don't have a leading 1 in row 2. So to get that, I need to take row 2 and divide it by negative 2. So that should give me 0, 1, minus 1 for row 2. Row 1 is left alone. So finally, to get this in reduced row echelon form, I need to recognize that the best thing I need to do is to turn this 1, 2 matrix element into 0. So let's take a Xerox copy of row 2, multiply it by minus 1, and add that to row 1. So row 1 becomes altered. She becomes 0, 1, 0, 3. Row 2 is left alone. Okay, this is reduced row echelon form. So you're almost home. You need to determine the corresponding set of algebraic equations. And you can do that from starting from the bottom and working your way up. And in that case, x sub 2 is going to be minus 1, and x sub 1 is 3. So for this particular problem, you do have a unique solution. Let's go back again to the concept of rank. Last lecture, we learned how to take the rank of a matrix. I invite you to do that in this problem, and you'll determine that the rank of the coefficient matrix is 2. The rank of the augmented matrix is also 2. So you'll get a nice relationship between these two creatures, namely that their ranks are equivalent, and they both of those ranks equal 2. Or in this problem, 2 is the number of unknowns in the problem. And so everything is fine. And again, this is all news. I've done this problem before. What's new, what lecture 6 brings to the table, is let's go back and look at the coefficient matrix A for this problem. There it is. It's a square matrix of order 2. And now, again, let's recognize that this matrix has 2 columns, C1 and C2, but each of those columns are vectors. Excuse me. C sub 1 and C sub 2. And a simple observation you can make is as follows. There's no scalar alpha that you can concoct such that when you multiply it by C sub 1, you get the vector C sub 2. So what does this tell you? This tells you that C sub 1 and C sub 2 are linearly independent. Now again, this is not a proof I've just gone through one example, but this is highly suggestive of the observation that if you have a matrix whose columns are linearly independent, and you use that matrix as a coefficient matrix to solve for a set of unknowns in a set of linear equations, then in fact, you will always get a unique solution. So one exercise, and I probably will have you do this in problem set 6, is go back and look at, so revisit problems we have previously solved and explore the nature of the columns. So we explored A, the coefficient matrix, but specifically look at the columns of that coefficient matrix A and see if they are linearly dependent. You know how to do that, or linearly independent. And so independent. Let's get this typo out the way. Independent. Okay, so I've discovered something. Namely, if I write down a set of equations and a set of unknowns, and I start out with my coefficient matrix, it really consists of column vectors. And the question I want to ask is, what's the nature, what's the relationship between those column vectors? If those column vectors are linearly independent, then these 3 examples suggest that a unique solution to the problem will exist when you take that coefficient matrix and use it in an example. And if in fact those 3 column vectors are linearly dependent, then there's either an infinite number of solutions or no solution, but there certainly is infinite number of solutions or no solution, but there definitely, there will be no solution. Okay. So this is sort of interesting. And again, in problem set 6, you'll get an example to look, you'll get an opportunity to explore this in a little bit more detail. Okay, we're still talking about vectors. And we spent a lot of time talking about matrices. So I next want to show you that vectors can actually be expressed as matrices. So here's the connection. Up to now, we've been looking at matrices as creatures that walk on down one side of the street, vectors as creatures that walk down another side of the street. Turns out these guys are related. So let's pick an example in 3-dimensional space. So here's a vector V. Its coordinate representation means that you can write it in terms of 3 scalars: V sub x, V sub y, and V sub z. And you can plot these guys. Now, I can write this. I can write this vector V as a matrix. So what am I talking about? Well, if I get rid of the commas, then this thing really is just a 1/3 matrix. And the symbol on the left, I really technically should write this as a matrix. Well, there's a tilde underneath, but I'm not going to do that. The convention is that, even though it's a matrix, I still am going to use my vector notation. So when I do this, I'm writing a vector in what's called row representation. So this is a row representation of a vector. It's a 1/3 vector, has 1 row and 3 columns. And again, even though this guy technically is a vector, I still will express it as a vector. So, sorry, even though this guy technically is a matrix, I'll still write it as a vector. Now, you could choose to write your vector not in row representation, but in column representation. Namely, you could write this vector, which again, in coordinate representation looks like this. Let's not forget what this is. This is coordinate representation of a vector. But here I could write this as a column vector. Or a column, or a matrix. This matrix has 3 columns, 3 rows, and 1 column. So let me tell you what people typically do. You have to make a choice here. The standard choice that everybody does, and we will not be exceptional, so we'll do it, is we'll express our vectors in column representation. So this vector can be written as a 3/1 matrix. Hence, you see the title of the introduction to this section, all vectors can be written as matrices. It is not true, so this is true. It is not true, and you should think about this for a minute, that all matrices can be written as vectors. That is not true. The operative word is all. Okay, so this is going to be very useful when we revisit this problem of multiplying matrices or multiplying vectors. So let's look at an example. Suppose I have 2 vectors, u, and I'll write this in a coordinate representation. And let's say I have another vector, v. The commas tell you that I'm dealing with coordinate representation. So this is coordinate, I'm writing this in coordinate representation. The next thing I want to do is take these vectors and express them as matrices. And again, the convention is we'll express them using the column representation. So what does that mean? It simply means that U is a 3x1 matrix that looks like that. It has 3 rows and 1 column. The matrix V is also a 3x1 matrix. She has 3 rows and 1 column. So what does it mean when I multiply, bad word, when I take the dot product, better word, of these two vectors? So what is the dot product or scalar product, or as we'll see later on, inner product? All these terms are the same, of those two vectors U and V. Well, let me write down the answer. I know what the answer is. The dot product of U and V is just U sub 1 times V sub 1 plus U sub 2 times V sub 2 plus U sub 3 times V sub 3. The question is, how would I get that from writing these vectors in column representation, making sure that I obey the laws of matrix multiplication? For example, you could simply not do this. You want to take these two matrices and multiply them together, both in column representation. You're in trouble. First matrix has 3 rows and 1 column. Second matrix has 3 rows and 1 column, and you can't multiply these. You can't multiply them because the column index of the first matrix is not the same as the row index of the second matrix. But what you could do is take the transpose of the first matrix. Where this first matrix has 1 row and 3 columns, the second matrix has 3 rows and 1 column. The column index of the first matrix is identical to the row index of the second matrix. And if you use the ordinary rules of the regular rules of matrix multiplication, you'll get the right answer. Remember, you just multiply the first row of the first matrix by this first column of the second matrix, and you just multiply those matrix elements together, each one, U1 times V1 plus U2 times V2 plus U3 times V3. Now, what's a simpler way to write this? Well, this is just the transpose of the matrix U multiplied by the matrix V, and that is the same as the dot product of U with V. So this is so special. We'll give it a box of its own. If you take the dot product of two vectors, that's the same as just multiplying the transpose of the first matrix times the transpose of the first vector in matrix representation times the second vector in matrix representation, where we are writing these vectors in column representation. That's the standard. That's what we'll do. Okay. So this is a nice way to go from the idea of vectors to the idea of matrices. as far as the dot product is concerned. So I will leave the following up to you. What happens if you take the dot product of U with V? First of all, I know it better give me the same answer as taking the dot product of U with a V. So actually that's a simple thing that I'd like you to first prove. Prove that this is true. Prove that the dot product is commutative. So that's number one. The second thing I would like you to do is figure out what is this in terms of matrices. Is it this? Or is it this? Or is it neither? So this is an example of a problem that, or exercise that if you go through it and take the time to work through, when you get the answer, you will have learned a lot, okay? So I'm not gonna tell you the answer, but it's a useful exercise to go through. Okay, so let's review where we are right now. We have looked at unit vectors and realized that these guys are basis vectors. And we've done this for R1, the line, R2, the plane, and R3, three-dimensional space. We've introduced the idea of the linear dependence of vectors. And we've defined what we mean by that. We've defined what we mean by the linear independence of a set of vectors. And we've shown that Gauss-Jordan elimination can solve both of these cases, 2 and 3. And last but not least, we've shown that all vectors can be written or expressed as matrices. So there's a connection between matrices and vectors. And the convention is we will always write these matrices in column representation. So for example, if I have the matrix A, which looks like this, and I have, if I have the vector A, which I can write as a matrix that looks like that, and I have a vector B, which I can write as a matrix that looks like this, I can take the dot product of those two matrices, of those two vectors, and that's simply the transpose of the first matrix times the second matrix. There is no dot here. That's not a typo. Here, this A is a vector. Here, this B is a vector. And even though I've given these guys arrows, these two creatures on the right-hand side are really matrices. They are matrices written in column representation. Now, you will have ample practice in dealing with writing vectors as matrices in problem set 6, especially in the Python exercise. So let's take a minute to wrap up. What's next? Well, I do not know the answer to this question. So what does the vector 1, 3, 7, 5 look like? I don't know how to draw that vector, because in order to draw that, I don't need the coordinates of a line. I don't need the coordinates of a plane. I don't need the coordinates of three-dimensional space. I need to find the coordinates of four-dimensional space. And my brain, as well as yours, can't help us out. We don't know how to do that. But I could always write this vector as a matrix that has 4 rows and 1 column, or as a list. So we're going to see next time that we can talk about vectors in 13 dimensions. We can talk about vectors in 256 dimensions. We can talk about the magnitude of those vectors. We can talk about their dot products. We can add vectors together that exist in 16 dimensions or 4 dimensions or a million dimensions, but we can't write them down as arrows because we don't know how to write down a nice cogent picture in 4-dimensional space or 5-dimensional space or n-dimensional space for that matter, because our brains just don't work that way. So we're going to look at vectors not in 1, 2, or 3 dimensions, but in n dimensions. And it's going to be a very useful reason why we're going to do that. So that concludes lecture 6 for today.